Today it is our first video lecture on electrostatics, and today we shall discuss about some fundamental properties of electrostatic induction, and also our first principle in electrostatics, that is the Coulomb's law. আজকে Coulomb's law নিয়ে আমরা আলোচনা করব মেইনলি, মাঝখানে আমি ইলেকট্রোস্ট্যাটিক্সটা একবার বলবো। ওকে, ইলেকট্রোস্ট্যাটিক ইন্ডাকশনটা একটু বলবো। আচ্ছা, electrostatic induction is the process when a charged body is brought near to a conductor. Then in the nearest end of the conductor, opposite charge is induced, and at the farthest end, same polarity charge is induced. It is because that only it will be available in case of the conductor, because we know that in case of all the conductor there are larger number of free electrons available. And you all know that in case of a conductor, the larger number of free electrons may be in the order of 10 to the power 19 to 10 to the power 22 per unit volume per cc. Okay, and this free electron comes from the last electronic orbit of the concerned atoms, over which the nuclear electrostatic force effect is very much less. So they are the weakly bound electrons. These electrons actually moves in the interatomic spaces of the conductor, and their behavior can also be explained by some gas laws, preferably gas laws. So these electrons are also known as electron gas also. Okay, and the motion of these free electrons is just like a random zigzag and eternal motion, and it is known as the Brownian motion, Okay, now in case of a conductor, so there are large number of free electrons, but whereas in case of an insulator, the number of such free electrons is negligibly small. Okay, now when a conductor is brought near to a charged body, now we all know that charged body produces an electric field. Now this electric field, it may be assumed to be uniform. Okay, so under this electric field, the free electrons will experience a force, and so they will be accelerated, or they will get a drift velocity. And you all know, when the electron moves in a particular direction, the region from which electron moves to the other region, the region from which the electron moves, their positive charge is induced, and the electron and the region in which the electrons are gathered, their negative charge is induced. So there will be a relative charge separation in case of the conductor. So at one end, if some positive charge is induced, that means this region is lacking the number of free electrons, and whereas in the other region electrons have been gathered on the effect of the electric field being applied by the external charge body, here the negative charge is induced. But you all note that the total amount of charge will be zero, because the conductor will be always electrically neutral. Okay, now the physics of a charge carrier when it is in the stable position, or when it is at a rest with respect to some arbitrarily chosen frame of reference, is dealt in the branch of electrostatics. Now we are now discussing about the most important and preliminary law in electrostatics, which is known as Coulomb's law. Let two point charges, one is Q1, another is Q2. One is Q1, another is Q2, are separated by a distance, say d, are separated by distance d in air. Okay, now if you all know, if they are same polarity charges, then they will repel, and if they are opposite polarity charges, then they will attract. That means if they are both positive or both negative, then there will be repulsion, or if one of them is positive, another is negative, then there will be an attraction. If the force of attraction or repulsion, that is the force of electrostatic electrostatic interaction is represented by F, then F proportional to Q1 Q2, and F inversely proportional to the square of the distance between the charges. Therefore, combining these two laws, we have F proportional to Q1 Q2 by d square. F proportional to Q1 Q2 by d square. So a constant of proportionality will come into play. I am representing this constant of proportionality by K. So F equals to K into Q1 Q2 by d square. Okay, now If we consider the calculation in SI system and for free space, then K is written as K equals to 1 by 4 pi epsilon naught, where epsilon naught is known as the electrical permittivity of free space. Electrical permittivity of free space. Okay, and its value, it is given by 9 into 10 to the power 9 Newton meter square per Coulomb square. 9 into 10 to the power 9 Newton meter square per Coulomb square. So in SI system and for air medium, which is also represented by the free space, it can be written as 1 by 4 pi epsilon naught Q1 Q2 by D square. Okay. If instead of the air medium, some another dielectric medium is considered, then there will be a dielectric constant in the denominator. That is, instead of epsilon naught, or epsilon naught will be replaced by electrical permittivity of that medium. So electrical permittivity of that medium will be epsilon, that is epsilon naught into K. This K is known as dielectric constant of the medium. This K is known as dielectric constant of the medium. Therefore, F equals to 1 by 4 pi epsilon naught into K Q1 Q2 by D square. Q1 Q2 by D square. Okay. So it is for the other medium. Now, clearly from this relation you all see that K is a unitless and dimensionless quantity. Okay. Now, simply a new term is introduced here, that is the electrical permittivity of free space. And by simply the electrical permittivity of free space means, if we consider an unit area drawn normally at any point or about any point of any medium, say of the free space. I am again repeating, if I consider an unit area drawn normally about any point of the free space, then the number of lines of electrical force crossing through this area will simply represent you the electrical permittivity of the medium, of that medium. Okay, now you all see that this law is basically a vector law, because F is a vector quantity. So this law should be expressed in the vector form. Okay, now I am coming to represent this equation in the convenient vector form. এমনি রেকর্ড করছো না? তাই করে বলবে। Let the position vector of the two charges, it is Q1 and it is Q2, with respect to some arbitrarily chosen origin O, it is R1 and R2. Let it is R1 and let it is R2 vector. R1 and R2. Okay. Now, this is the position vector of the charge Q2 with respect to Q1, and in accordance with the triangle law of addition of vector, you have all learned it in your previous class, that is in the class 11, that it will be simply R2 minus R1. Okay. Now, force on the first charge due to the second will be equal to the force on the second due to the first, equal and opposite in accordance with the Newton's third law of motion. So let us now write the force on the first charge as exerted by the second charge. Now you must all remember that both the charges are stationary. That means with respect to the arbitrarily chosen origin, the charges are not changing their positions with respect to time. Okay. Now force on the first charge due to the second, let us represent it by F12. That means force on the first charge due to the second. I am taking this symbol. Okay. So it will be, you all know the force is a vector quantity which can be represented by the magnitude of the product of the magnitude of the force into the unit vector in the constant direction. That is 1 by 4 pi epsilon naught Q1 Q2 by modulus of R2 minus R1 square It is the magnitude of the force. You all know that is, I have already represented by in free space, that is 1 by 4 pi epsilon naught q1 q2 by square of the distance between the two charges into, I am writing it as vector, just a unit vector. That is an unit vector. So R21 cap is an unit vector in the direction of the second charge as measured by the first charge, or it is in that direction. And I am giving you a negative sign here. So this law is it can be again written as 1 by 4 pi epsilon naught q1 q2 by modulus of r2 minus r1, that is square, into r2 vector minus r1 vector, and unit vector is obtained by dividing the vector, constant vector, by its magnitude by mod of r2 minus r1. Okay, so it will be minus 1 by 4 pi epsilon naught q1 to q2 r2 minus r1 by mod of r2 minus r1 cube. Okay, you all note that when r2 minus r1 is positive, when r2 vector minus r1 vector is a positive sign, the force is negative. That means when it is positive, the force is negative. When it is positive means the force is negative. What does it indicate? Force on the first charge due to the second is positive. That means it is in case of when r2 minus r1 is positive, the force is negative. That means the force is in the direction. Is in the direction of in this direction, or it is of the opposite direction as that of r2 minus r1 vector. That means force on the first charge will be in this direction. That is, the force is repulsive. So when r2 minus r1 is positive, force is repulsive. When r2 minus r1 will be itself negative, that means negative negative positive, or the force will be attractive. Negative sign bears only this significance. I am again repeating you at this point, explaining at this point that look, when r2 minus r1 is positive, this is positive, overall force is negative. That means force will be in that direction, or it will be opposite direction as that of r2 minus r1. So force will be repulsive. But if r2 minus r1 itself is negative, then the force will be positive, or it will be in this direction. That means the force will be attractive. Okay. Now, under this situation, if the mass of the first charge is m1 and the mass of the second charge is m2, and if I am asked that both charges can move only under the force of electrostatic attraction or repulsion, that is electrostatic interaction, then the acceleration of the first charge, it will be a1. That is simply by a1. Similarly, acceleration of the second charge, f by m2. Now, what will be the acceleration of their common center of mass? Now, the acceleration of their common center of mass can be written as AC, that is m1 a1. You all know acceleration of the center of mass m2 a2 by m1 plus m2. That is f1 comma 2 plus f2 comma 1 by m1 plus m2. It is 0. Why it is 0? Because according to Newton's third law of motion, f12 is nothing but minus of f21. So it is 0. So only the electrostatic force of interaction acting between two charges cannot produce any acceleration of the common center of mass of the charges. Okay, clear? Obviously, I have restricted my discussion in case of two charges only. Okay, until now, until I have just discussed the basic definition of electrostatic induction and also the statement of Coulomb's law only. Okay, we shall meet in the next class.